You know, we all see AI getting smarter and smarter, but have you ever just stopped and noticed that little pause before it answers you? Well, behind the scenes, there's this huge battle going on to make AI not just smarter, but way faster and cheaper. Today, we're going to pull back the curtain on one of the biggest hidden bottlenecks holding it all back and the incredibly clever ways engineers are trying to fix it.
So let's start with the big question, right? You ask a chatbot for something, and you see those three little dots, typing, typing. Why? If these models are so incredibly powerful, what's taking so long? Well, the answer is kind of baked into the way they actually think.
These large language models work using something called auto-regressive generation. Now, that's a super fancy term for a really simple idea. They write one word at a time. And to figure out the very next word, the model has to look back at everything that's already been said in the conversation. Just imagine trying to text a friend, but before you type each new word, you have to go back and reread the entire chat history from the very beginning. It's wildly repetitive, and for a computer, it is super, super expensive.
Okay, so that glaring inefficiency was just too big to ignore. So engineers came up with this really brilliant workaround. It was the first major fix to speed things up, but as we're about to see, it created a whole new kind of problem, a very hungry problem. And here it is. Meet the KV cache. The easiest way to think about it is like a short-term memory for the AI. Every time the model does the math for a token, it just stores the answer here. So instead of rereading and recalculating the entire chat history for every single new word, it just glances at its notes in this cache. This one trick completely changes the game. It trades raw computing power for memory, and it makes generating text dramatically faster. But here's the crazy twist. This short-term memory, it's incredibly hungry. How hungry are we talking? Well, for a cutting-edge model like Llama 3, serving just 32 people at the same time, the cache alone needs a jaw-dropping 83 gigabytes of super expensive GPU memory. That is more memory than most high-end gaming PCs have in total. And this right here is the new problem. Our brilliant solution to the compute bottleneck created a massive memory bottleneck. The AI's short-term memory often ends up taking more space on the chip than the AI's actual brain, the model itself. So the really crucial thing to get is that optimizing AI isn't just about model size anymore. It's become this frantic race to manage memory.
So, if the cache is the problem, how in the world do the big cloud providers, the ones with endless data centers, handle this memory crisis? Well, it turns out there's not just one answer. A really fascinating new research paper actually breaks it down into 3 competing philosophies for taming this beast.
And what's so interesting here is that there's no single best way to do it. It's just a series of really tough trade-offs. On one end, you have VLLM. Think of it as the speed demon. It's all about raw performance, keeping everything in that expensive GPU memory, which makes it a total memory hog. Then you have H2O, which is just ruthless. It permanently deletes parts of the conversation it thinks aren't important, which saves a ton of memory, but risks giving the AI a bit of amnesia. And finally, you've got InfiniGen, which tries to have it all by offloading the full cache to slower memory and just pulling in what it needs. It keeps the model accurate, but man, it pays a huge price in speed. This chart really puts those trade-offs into perspective, doesn't it? If you look at throughput, basically how much work you get done, for every single gigabyte of that precious GPU memory you use, H2O is the clear winner. Its ruthless strategy of just kicking tokens out gives it the most bang for your buck when memory is tight.
But what's the cost of all that efficiency? I mean, what good is a fast AI if it can't remember the name of your dog? Researchers tested exactly that. They tell a model a fact early in a long chat, like, "My dog's name is Barkley." InfiniGen, which can pull old memories back, remember the fact over 92% of the time. But H2O, a huge drop in accuracy. It literally forgets. Its efficiency comes at the very real price of memory loss.
Okay, so that's the high-stakes world of giant data centers with endless GPUs. But what about running a powerful AI on the machine you're probably watching this on right now? The challenge is kind of the same. Not enough memory, but the solutions, they are completely different.
This quote from Microsoft's Dave Raw just nails it. When it comes to local AI, you can't just cleverly manage a giant cache in real time like you do in the cloud. You just don't have the horsepower. The battle has to be won before the model ever starts running. The entire goal is to make the model and its cache fundamentally smaller from the get-go.
And the number one weapon for this is a process called quantization. The best way to think about it is like creating an MP3. Right? You start with this huge, perfect quality wave audio file, and you compress it down into a much smaller MP3. You lose a little bit of sound quality, sure, but now it's small enough to fit on your phone. Quantization does the exact same thing to AI models. It just reduces the precision of all the numbers inside to drastically shrink the file size.
For all the enthusiasts out there running models at home, this has become a pretty standard workflow. First, you convert the model into this universal runnable format called gguf. Think of it like a .zip file for AI. Then, you use a special tool to shrink that file down, picking a compression level that balances size and quality. But then there's this optional third step, and this is where the real magic happens. It's called an importance matrix, or I matrix. Let's go back to our MP3 analogy. Using an I matrix is like giving that audio compressor a special note that says, hey, when you're shrinking this song, I don't care what you do to the drums or the bass, but you have to protect the lead vocals at all costs. The I matrix does that for the AI, identifying the most critical parts of its brain so they're preserved with higher quality during the shrinking process. The result? A much, much smarter small model.
You know, this whole process of juggling models and drivers and hardware, it used to be an absolute nightmare. It was messy and super complicated. But now we're seeing this entire optimization pipeline get built directly into our operating systems. Platforms like Windows ML are designed to take all that chaos and just automate it, making it way simpler for any developer to bring powerful AI right to your PC.
So, we've seen the two extremes, right? The massive, dynamic world of the cloud and the small, pre-shrunk world of the PC. Now let's try to bring all these ideas together into one unified concept.
This really sums up the two philosophies perfectly. On the server side, you assume the model is full size, and you use all these sophisticated tricks like page detention and sparsification to juggle its huge memory needs for thousands of users. But on the PC side, the goal is completely different. You use methods like quantization to shrink the model so it can fit comfortably on just one machine. Two different battlefields, two totally different sets of weapons.
So here's the most important takeaway from all of this. There is no single silver bullet for making AI efficient. Instead, what engineers have is this rich and growing toolkit. And depending on the problem they're trying to solve, they can pull out different tools. Whether it's clever memory management for the cloud or aggressive compression for your laptop, it's really all about picking the right tool for the job.
And this quote from those researchers we looked at earlier just says it all. This isn't about finding one right answer. It's about constantly navigating a three-way trade-off between memory, speed, and accuracy. Every single optimization technique we talked about today is really just a different choice along that spectrum.
Which kind of leaves us with one final big thought. For years, the race in AI has been all about making models bigger and more capable. But maybe, just maybe, we're entering a new era. As these models start approaching superhuman intelligence, is the real frontier, the defining challenge for the next decade of AI, no longer about making them smarter, but about making them radically, fundamentally more efficient. It's a question that's going to shape the entire future of this technology.